That is very good. Nice job. Okay, so to check yourself with this, you go to the periodic table, determine the atomic number 16, you add the electrons. This doesn't equal 16, so it's wrong. So you're going to try again for us, Heather?
I don't know how to do
You know how to do you don't know how to do sulfur?
I meant sulfur. I don't know how to do sulfur.
Okay, so you did sodium. Nice try. Anybody want to come up here and try to do sulfur?
Sulfur's what?
Sulfur is S. You have 16 electrons to place.
I see where sulfur is.
Cody's gonna try it.
Yeah, I think so.
Cody, you can come on down.
But I still kind of don't understand the electron configuration thing, but
Right, so you can see that the shapes have a maximum number of electrons that can be placed. The S is 2, the P is 6, the D is 10, and the F is 4. This corresponds to the number of shapes that each one has. So the P has 3 shapes, the PX, the PY, and the PZ, right? Remember that? The S only has 1 shape because that's why it has 2 electrons. This one has 3, this one has 5, this one has 7. So 7 times 2 is 14. So they're getting 14. Does that make sense?
yeah.
Right, so this right here is what's wrong. Cody, can you fix that for us? Here comes Cody.
Feels weirder with the.
I know, I'm trying to get used to this laptop. I left my GoPro at home. I'm struggling. It took me like 30 minutes to figure out how to get audio on this. Because the software I'm using has a selection for audio. It took me a while to find it. All right, that is correct. Nice job, Cody. Excellent. So elements lose and gain electrons to become stable, and when potassium loses 1 electron, it's going to behave like argon. The correct answer for these ions, the electron configuration, they're going to behave like the noble gases. When they lose electrons, they want to be noble. We just did the configuration for iron. Iron 2 positive. It has 26 electrons as an element. So I'm going to go and I'm going to place the noble gas configuration of argon. That's the first 18. So I'm not going to write all the first 18 because I don't need to. It's just a lot of work to do. And now the rule up here says, these are the 2 possibilities. I'm going to stick with the first one. N is the energy level, so it's on the 4th energy level, that is. If you look, iron falls in the 4th energy level. So you'll see 4 there in the book, on the 4th energy level. So we're going to say 4s0, following this pattern, 4s0. And then we're going to say the next one is the energy level. It drops down to 3. If you remember from yesterday, you have your 3d. Iron is on the 3d. So it becomes 3d. And then I'm going to lose 2 electrons. So I have to count the total number of electrons on this level here. And there's 1, 2, 3, 4, 5, 6, 7, 8. So there are 8 electrons that we're dealing with past argon. So there's 8 electrons past argon. So there's going to be 6, and we're going to lose 2 because of the 2 positive charge. So this is going to be your formula that you're going to show. Now that's a little bit complicated. I'm not going to lie to you. It's very difficult to come up with a cheat sheet like we showed you on the first day where you have the 1, 2, 3, 4, 5, 6, 7 and the S's and the arrows draw down. Right. It's very difficult to do that. You just have to know that these are the formulas. That's why we gave them to you yesterday. I'm not going to test you on them. I'm just showing you that they exist. Right. Argon equals 18 electrons. And when you form manganese plus 7, it's going to lose all 7 electrons in the outer energy level, and it's going to behave like argon. Is it the most, I guess you'd say, common oxidation state for manganese? If we look on this paper, it says common N. It just says that it's common. It doesn't say it's the most common. Well, actually, it says manganese 2 plus is the most stable. Manganese 2 plus. So manganese, you would think this would be the most stable, but it's actually not. And manganese plus 7 is not the most stable. Manganese +2. So let's just do +2 real quick. So let's write that out. Right, so its configuration is going to be very similar to iron 3. They're actually going to mimic each other as far as their configuration. Their behavior will be very similar. Now, their physical property will not be the same. Why?
Because they're two different elements.
Because of what?
Because of
Starts with a P.
protons.
Because of the protons. Very good, Garrett. Okay, so we're doing this Lab A's indirect method of determining the dimensions of a molecule kit.
We should just not do work.
So if you know what you're doing, I'm going to go ahead and let you get started. We just read it. So let's just...
Be careful transfer blah, 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 blah. Yep, it doesn't say anything about couple of them.
Oh, I did
Are you getting the measurements here correctly?
There you go.
Oh, that's really nice. Now it has to be level. The ball bearings need to be level. The level ball bearings.
Is that pi?
You take the radius and
Yes, it is pi.
you do radius times 2, your diameter times 2,
Okay, so I was going to go into the lab this week, but there were... Do you have the height yet?
No, because I see, but
Yeah, you're going to calculate the height.
how do you do that?
Well, that's difficult.
Oh, yay. Okay, so
You need the volume to calculate the height.
Right, but you can calculate the volume with your graduated cylinder.
Oh, so 7.
Right.
Okay.
Your volume is 7 milliliters.
Got it.
Yeah.
I got it.
Now, the back of your sheet, you've got the, find the things that are wrong with the periodic table. The first periodic table John Newlands put out, he had only like 3 things correct. That is his placement. He only had 3 things that were correct. This table, I can just look at it and tell you number 19, potassium, the symbol is not JK.
Oh,
So I've given you
okay.
one for you.
Just kidding.
Right. Number 8, oxygen is not OMG. All right, so I've given you 2. So it's not that difficult. Don't think, oh my goodness, Mr. Stonecker, this is going to be hard. If you look here, we've got 3 examples of potassium. Potassium is the ion. It loses an electron. It loses this electron, so it can behave like argon. Argon is a noble gas. You can write it 2 ways. You can write it as an element, K, 19 electrons, argon, 4s1, or you can go 1s2, 2s2, 2p6, 3s2, 3p6, 4s1. Now it's argon because argon, if you look at the electron configuration for argon, argon has 18 protons. So you got 2 here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. If you notice, it's got 8 electrons on the outside. And this is what allows argon to be stable. All 8 electrons are paired up, moving in clockwise and counterclockwise positions, symmetrically around the nucleus. So these are going to be in symmetry around the nucleus, providing it the ability to stay stable. Okay, Zane, very good. So this is silicon. How many electrons have you placed?
Electrons are just like the numbers of these, right?
Yes, you got 2, 4,
10,
10,
14.
14. So if you look on the periodic table, is the atomic number for silicon 14?
Yes. It is.
Excellent. So we know that we are correct. Nice job. Can anybody do bromine?
It is therefore necessary to use an indirect method to make the measurements. Precision.
Of your lab, there's a periodic table of mistakes. A first mistake that you'll notice is number 19, potassium is not JK. It's actually K, so I'm giving you an answer. Number 8, oxygen is not OMG, it's O. Now the first periodic table that was ever published by John Newlands February 7th, 1863, had only 5 correct responses. He had hydrogen placed in the correct period end group, lithium correct in the correct period end group, and magnesium in the correct period end group. And those are shown to you in green circled. Does everybody see that? Group 7, iodine is placed in the correct group, and group 6, is that tellurium? Tellurium is placed in the correct group. So John Newland's got 5 of the correct elements placed in the right group. He did predict an unknown element, and we'll talk more about that later. Okay, this is the shortcut method that many people have used for quite a while. First thing you do is you number from 1 to 7. I left off a 7 there. So 7. That's an S. And then you go from 2 to 5, 3 to 4, 3 to 5, and 4 to 5. And that's S, P, D, F. And you're just going to go in this direction until you fill up all of your electrons. So you have 35 to place. So you're going to go from the 4S over here to the 3D, which you see right here, 4S, 3D, and then from the 3D to the 4P till we get to 35. This is a pattern you can use when you're taking a test. If you're in a bind, you will not be given a periodic table like this on a test. So the one that you colored on Monday, you will not be given one like that on a test in college.